Why you turn the light on?
Oh.
You can
It's
turn
on.
the light on.
It's on.
How do you turn it on?
There's a button there that says light.
Sweet.
In this house, we obey the laws of thermodynamics.
What's that from?
Simpsons.
That is Homer.
I'm just gonna guess this.
I don't like it.
That's when Bart went to a different dimension, and it made Homer real mad.
That would make me mad.
Okay, what we're doing this chapter is we're talking about energy.
How'd you do that?
And energy is used in the cell for a lot of different things.
Drop something.
That's what she said.
The cell basically takes energy that comes from sugars. Sugars like glucose. You remember glucose? And the cell has an organelle that rips sugar into pieces. And whenever you take a molecule like glucose,
Kind of like what the mitochondria does.
whenever you take a molecule like glucose and you rip it to shreds, energy flies out of it.
That's just like a mitochondria.
The mitochondria is
not
the
funny.
organelle that takes this
Take that
glucose.
first.
Take what?
You heard me.
Listen, let me do this. The mitochondria is the organelle that takes the glucose, tears it apart, and when the glucose is torn apart, energy comes out, and the energy is stored in a special molecule that we call ATP. ATP is known as adenosine triphosphate. So we're going to learn about that. So the book starts out by talking about the laws of thermodynamics. Let's talk about those for a minute, because it's important to understand the way energy works, to understand a little bit about what energy is. The first law of thermodynamics says that energy can be converted from one form to another, but it cannot be created nor destroyed. Do y'all remember that from physical science?
Yeah.
Yes, what were you going to say, Meredith?
If you're going to put that on a flashcard, could you just call it like first law of thermodynamics?
Or you can just put it in your notes instead of a flashcard.
Yeah, you can do either.
I think flashcards like taking something.
Now, let me give you an example.
Yeah. Just like,
Because I'm holding this thing up, listen, because I'm holding this thing up, it has what we call potential energy. Potential energy is basically energy that's stored within something that can potentially be converted to another form.
Kinetic energy.
The form I'm going to convert it in is to kinetic energy, which is energy of movement. But I just did it. It went from potential energy stuck to kinetic energy moving.
that's crazy.
And so I can convert it from one form to another pretty easily just by dropping it. And that's the first law of thermodynamics. Energy can never be created out of nowhere or destroyed, however. Energy just changes forms. You can go from chemical energy to heat energy. You can go from light energy to chemical energy, which we'll see is done in the chloroplast. Yes?
If I was laying on the floor,
Yes.
what kind of energy would I have?
Well, you would have potential energy if you consider where you're laying to an object that's lower.
Laying in the road.
Probably taking.
If you consider that you can't go any lower, like in a hole or something, dug down in a hole like that, then no, you don't have any more potential energy. And no kinetic
what kind of
energy
energy
because
would
you're
you
not
have?
moving, so you don't have any.
Sweet.
No.
So I can just create it out of nowhere if I stood up out of nowhere.
No, because you're not creating it out of nowhere. You're creating it from tearing down glucose molecules that you ate with your food.
And your muscles use it.
How's that for an answer?
And then that converts chemical energy to kinetic energy. The chemical energy that's stored in the food.
Okay, how is energy made if it cannot be created?
Well,
Can't be destroyed
like,
either.
Is there like
God.
one
Don't
energy
breathe, I
in the
think
beginning of
that's
time
That's correct.
that's converted
That's
forever?
correct. That's correct.
Wow.
Yeah.
That's weird.
There was energy present at the beginning of the universe.
That's crazy.
And where did that originally come from?
God.
Glucose. Jesus.
Alright, listen.
Jesus.
The second law of thermodynamics. Okay. The extra conversation has to stop. It slows us down. Okay, I've been over this before. Quietly. Second law of thermodynamics, energy cannot be converted without the loss of usable energy. Whenever you convert from one form to another, you lose some of the usable energy. For instance, if I break this molecule apart, the energy comes out of the bonds of the atoms there. The bonds present between atoms of the molecule. If I break this apart, energy will come out, and that energy will be captured by another molecule. But in doing that, I lose some of the energy as heat. It's not destroyed, but the energy that I can use from the process goes away as heat and goes into the atmosphere. It's not usable anymore. And we have a term that talks about the loss of usable energy. It's called efficiency.
We need to close up.
And there's usually a percentage attached to efficiency. Percentage efficiency. And any type of energy converter, we can discuss this. For instance, an engine in your car. An engine in your car takes the energy, the potential energy stored in the gasoline, and converts it to movement of your car, to your car going forward. But it's not very efficient. It's only, most car engines, that kind of thing, are only about 10% efficient. That means 10% of the energy of the gasoline is moving the car forward. The other 90% of the gasoline energy is lost as heat. And that's why the car gets hot, the engine's hot. And a lot of the energy just goes away as heat, and that energy is not usable. So, the percentage efficiency of cells is a lot higher than of car engines. It's about 40%. So when we tear apart a molecule of glucose and store the energy coming out of that, we're at about a 40% efficiency. 40% of the energy is stored and able to use by the cell, and 60% of the energy is lost and not usable. It's lost as heat. Heat is usually the way energy is lost in systems. You are doing chemical reactions right now inside your body, and a lot of the efficiency from those reactions are around 40%. They're pretty low, and there's a lot lost as heat, and there's proof of it. You know what the proof is that that's going on in your body right now? What's that?
Or warm-blooded.
We're warm. Your body's warm.
Dang, how'd you know that?
That's right.
You can feel
That's
your
right.
face. It's warm. That's proof that reactions are going on in your body.
What if you're cold?
If you were dead, wouldn't be warm.
What if you're cold?
No chemical reactions. You're still warmer, even if you feel cold. You're still warmer than the outside temperature.
That's why
But
we kill a deer in the winter
if your body just varies by a slight degree, maybe 0.2 degrees, if your body gets a little cooler, you'll feel cold. And then you'll start shivering, and that creates heat, and that warms you back up. So just a slight variation in body temperature will cause a feeling of cold or hot. If you run around for a while, your body temperature does go up slightly. It goes from 98.6 maybe to 99. Just 0.4 degrees, and that will make you feel hot if you're just up a little bit. And you'll start sweating, and that'll cool you back again.
Wow.
Video footage?
Is that homeostasis?
Homeostasis.
Homeostasis is the process of maintaining balance in the organism's internal environment.
Ready?
Wow.
Oh, video.
Okay, quiet please.
Energy.
Whoa.
It's one of those words that we all know, but is still hard to define exactly. Still hard to say exactly what it means. We know that what keeps the universe running, and that without it there could be no life, that nothing could get done. But still, energy is a word, a concept that is shrouded in mystery. What really is this thing, this unknown force
so
called
fast.
energy?
Quiet, please.
As we'll see shortly, that's not an easy question to answer. Of course, it's not hard to think of numerous examples of energy at work. The sun, our solar system's driving force. Animals in motion.
Chipmunks.
And the movement of cars along a busy street are all examples of energy at work. But what is it about them? What common thread do these examples share which allows us to say that all these very different things are examples of the same thing? That they are all examples of energy in use?
Drew, how was that video?
It's not going to
How
tell
was that
us.
video?
I like feel like chill.
It's alright.
It's alright.
Probably because there's deer in there and I wanted to kill it.
What the little burrowing thing?
I don't
It's called a
know.
chipmunk.
I thought that was. I think that thing got cut off. It's supposed to be longer.
Cute.
Okay. Let's talk about two of the main ways that energy
ladybug.
is used, and it's by organisms. Most of the energy on the planet that's used by living things comes from the sun.
Yep.
There's a little bit of energy that comes from geothermal from the earth, which is hot on the inside. But most of it comes from the sun. Tuck. The sun shines light that's captured by autotrophs. Autotrophs are plants or algae that do photosynthesis. In the cells of an autotroph are organelles that look like this. What is this called?
Thylakoids are inside of it.
The chloroplast.
Thylakoids are inside of it.
Thylakoids are these membranes right here. Very good. And what's on the membranes of the thylakoids? Chlorophyll, which takes in the sunlight and makes it into glucose.
G-Coast.
With the help of two molecules. Do y'all know what two molecules the sunlight is used to put together to make
Fire.
glucose? Now, these are called thylakoids. But the thylakoids take two common molecules
Meredith just said
and
fire.
use the sun's energy to put them together to make this.
I know it.
Yes.
Water, carbon dioxide, and sunlight.
Water and carbon dioxide. So water, carbon dioxide, and sun combine in this to make
This.
sugars.
Sugar.
That's photosynthesis. That's what this is made of. Water and carbon dioxide. Those molecules get put together to make glucose. And then the glucose is stored in the leaf. Or sometimes in the stem, like a potato. And then the heterotrophs, like animals, like bugs, eat the plants and get the glucose from the plants. And we call them heterotrophs. And then bigger heterotrophs will eat smaller heterotrophs, and so on. So we have the food chain.
When is it made into ATP?
That's a good question. That's what's next. So the original source of glucose molecules are plants. You get all of your glucose from plants, all your sugars. You might be sitting there going, no, I don't, Mr. Ellis. I get sugar from cereal I eat, or
Red Bull.
or I eat some candy. Well, that originally came from plants. All the sugar originally comes from plants. Sugar cane plants make that white sugar that they put into food.
Well, brown sugar.
Hey, 5 hour energy.
Even the brown sugar.
though.
Doesn't
No
use
sugar,
it.
no caffeine.
No
No
caffeine.
caffeine.
No caffeine.
It's a natural. It's a natural 5-hour boost.
It's natural.
Here's the word metabolism. Let's hear what it says.
Metabolism. Metabolism refers to all of the chemical reactions that occur within an organism.
Very nice. I like that guy's voice.
I hate it.
How do you get a high metabolism?
Some people have higher than others. It has to do with the thyroid gland hormone.
So what's bad about having a high metabolism? Or no, wait, no,
You'll
that's not
die.
bad.
Not necessarily bad.
It
Wait, is that
doesn't make
this
you
thing?
feel
One bad
energy.
thing about it
That
is
makes
you
you
need more
digest. It makes you
food.
digest food. It makes you digest food faster.
Is that why people with like high metabolism are like, oh, you're skinny because you have a high metabolism?
That's right.
Okay.
Wait,
And I
what
met
about-
fun fact.
Wow,
That's cool.
Oh,
What?
I know someone who has an overactive thyroid
They could
gland.
just have a low
They're
metabolism.
skinny?
Yeah, really skinny.
Yeah. Okay, so here,
Just kidding.
so we know. Okay, it's my turn.
He's joking.
Graham, are you with me?
Oh yeah, I'm
Pay
with
attention.
you. Sorry guys.
We know that metabolism occurs inside cells. Metabolism are chemical reactions. And two of those chemical reactions we're going to study this chapter. The first is photosynthesis, and the second is respiration. Photosynthesis is the chloroplast building glucose molecules. That's photosynthesis. It needs sunlight to do it. Light energy from the sun is converted to chemical energy for use by the cell. This is the chemical energy.
That's my pencil.
Is glucose
Just
an
throwing at
organic
me.
molecule?
That's
Yes.
my pencil.
Okay.
It's a, what type of organic molecule? Carbohydrate.
Yeah.
Here, you got some cum.
Carbohydrate. Remember we learned about that?
I know.
Drew.
Milwaukee.
Drew, up
You
here.
got some cum on your
So
arm.
cellular division, where like mitochondria
know.
breaks apart.
Cellular respiration.
So where that-
Yeah, that's what I'm going to do next. Y'all listen. Cellular respiration is when this thing has already been made, it goes to this organelle, the mitochondrion. The glucose goes into the mitochondrion, and the mitochondrion tears apart the glucose. And energy is released. And that energy can be used by the cell. That's cellular respiration. So we have two things here. Photosynthesis, this thing is made. Cellular respiration, this thing is broken apart. The plant does both of those things. The plant first makes glucose, and some of the glucose is sent to the mitochondrion to be torn apart. That's respiration. Now, the molecule, after the mitochondrion tears this thing apart, energy comes out. Whenever you tear apart a large molecule, energy will come flying out of it. Think about a big car. If Godzilla picks up the car and rips it in half, it blows up. That's the same thing that would happen if you rip this molecule in half. It would blow up. The energy would come out of it. And the energy is captured by a special energy capturing molecule that we call ATP. ATP stands for adenosine triphosphate. Adenosine triphosphate. Why do we call it triphosphate?
Because there's 7.
1, 2, 3 phosphates. Woo. Now ATP is made from its pieces, which are called ADP, adenosine diphosphate, this,
True phosphate.
and P. ADP and P come together to form ATP. Watch how this occurs. Watch how this reaction occurs. ADP and P, right here. Are y'all watching?
A to the
Watch
A
'em.
to the P.
They come together
Yeah.
to form ATP.
Mr. George forgot to say click. You forgot to say click.
Watch it again. ADP and P come together to form ATP.
Click.
Now that takes energy. Where does the energy come from?
The mitochondria.
It comes from tearing this glucose apart in the mitochondria. It happens inside the mitochondria.
It blows up.
Here's what happens. In the mitochondria, glucose goes in, ADP and P goes in, the glucose gets torn up, releases its energy, the energy is picked up by ADP and P, and now it's an ATP molecule. The ATP molecule is like a little battery, and it floats around inside the cell. the ATP molecule comes out of the mitochondria and floats around inside the cell. There are millions of these put together because there's millions of these being torn apart. And the ATPs will float up to, let's say, do y'all remember those little motor molecules?
Yeah.
Remember the motor molecules that were crawling along like that?
the microtubules?
Remember that? Let's take a look at that real
No,
quick.
they're not microtubules. Yeah, they go across my
Cytoskeleton.
Computers can do that.
Woo! Hold on, watch this.
Woo, yeah.
A on this test.
Hold on.
Yeah.
What are the differences between plants and
Oh, let's see. Plant cells have a bigger vacuole.
The cell wall. They have a big cell wall.
Okay, we cut out the talking back there, please.
Computers can do that.
Computers can do that? Yeah, baby, yeah!
Austin Powers.
Best movie
Shaggy,
ever.
Shaggy.
Ah! Watch, let's watch this. Okay, let me inform you what this is. This is microtubules, part of the cytoskeleton, remember that?
In the cytoplasm.
That's a vesicle, a bubble that holds stuff. And this is a motor molecule. And what we're going to do, now they're going to flip this upside down in this video, but what we're going to do is we're going to watch that motor molecule move.
Computers can do it.
Did I just mess it up? Sorry.
Yeah, baby.
Yeah, but
Yeah.
Tucker. Okay, watch. This is the microtubule. There's the motor molecule. Watch the motor molecule move here.
Motor proteins cause movements of vesicles, organelles, and the cytoskeleton.
Watch it.
Kinesin is a motor protein that moves vesicles and organelles toward the plus ends of microtubules.
See how it's crawling along there? Now, how is it doing that? They're not showing you everything that's happening here. In actuality, for each movement of the motor molecule, one ATP is used. An ATP will float up to the little arm here, attach to it, and break apart and release the little bit of energy. And that little bit of energy will cause one arm to move. And so what it's not showing you here is a succession of thousands of ATP are coming up, attaching, and coming apart, and releasing their energy.
Oh, that's a permanent spell rank.
The ATP comes up.